All right, this video is on solving and graphing inequalities. That is the section that you should be turned to in your packet. So if you've not yet done that, please do so and be both watching and listening as we're going throughout this. Let's begin. All right, so just a reminder, the big ideas of this one: an inequality represents two math statements that aren't equal. That's why it's called inequality. And an inequality has infinitely many solutions. So there's a whole bunch of solutions to inequalities, all right? Equations have one solution. Inequalities have a whole bunch of them, all right? They can be a whole bunch of values greater than 3, for instance. So that's kind of the big points that we're gonna come back to this one. So let's go ahead and get started now, solving and graphing inequalities. Well, inequalities can be solved just like equations can be, but with a few exceptions. So if you remember in a previous lesson, we were solving one-step equations, and there was a few steps that we kind of learned to make that happen. Well, this is the same kind of thinking. We're going to solve them just like we did equations. This first step here, the variable must be alone or isolated on one side of the inequality. So the goal is, again, to get the variable by itself. And we'll ask ourselves a series of questions to help make that happen. But we want to get it isolated on one side of the problem. We will isolate the variable by using inverse operations. All right, remember, those are opposite operations. I'll remind you about that here in a moment. Whatever you do to one side, you must do to the other side. Okay, you got to treat them equally. And when you multiply or divide by a negative number, the inequality sign gets flipped. Now, to be honest, this one's not really going to pop up in this lesson, but this is true. And it will happen more so in 7th grade content than it will in 6th grade content. But it is definitely true, all right? So we're just not going to really see it in action this lesson. All right, a few things that I want to remind you about. Okay, the equal sign. The equal sign basically serves as a balance between two sides of a problem, all right? Now, that's when you're talking about equations. Something on the left equals something on the right. 3 plus 1, for instance, equals 4. 10 times 2, for instance, equals 20. So those are balanced, all right? That's why we have the picture of the balance here. But the rules were pretty simple. If you wanted to do one thing on one side of the equation, you also had to do it on the other. And we're going to see that again today with this lesson about inequalities. We want to kind of keep things the same. And to do that, you treat both sides the same. Now, those inverse operations that we just talked about, just remember that's the opposite operation. So for addition, it would be subtraction. For subtraction, the opposite would be addition, okay? These two go together. And it's the same for multiplication and division. If we want to undo multiplication, we would do division, and vice versa. If we want to undo division, we would do multiplication. Now, this was not in your notes, but this is just some reminders because we're going to call on these as we're going along. Now, one-step equations look like this, all right? Now, we've solved these. We remember how to solve them. We want to get the variable by itself, so we do the opposite of what's being done to the variable. Like we subtract 5 on both sides. We subtract 7 on both sides. Right here, we would divide by 3 on both sides. So that's how we solve the one-step equations. One-step inequalities are pretty much going to be the same approach, all right? Because we want to come at them the same way. We want to think about how to get this by itself, and we got to do that to both sides. We got to undo it on both sides of the inequality sign. So our approach will be very similar to what we've already done. All right, so let's go ahead and start with number 1. Solve each inequality, check your answer, and then graph the solution. So if we are starting with this one, n plus 5 is less than or equal to 16. The first thing we want to do is get the variable by itself. And so we kind of ask ourselves, what is happening with the variable? What operation is being performed to it? And it's being added with 5. So we want to undo that. And the opposite of adding 5 would be subtracting 5. So we subtract 5 from both sides. Again, whatever you do to one side, you do to the other. It worked with equations, and now it works with inequalities. So if I subtract 5 from both sides, this cancels out, and I'm left with n is less than or equal to 11. Now this tells me that my values that would make this true are anything that is equal to or less than 11. So I can check this now by thinking of some numbers that would work. If I think about a number line here, if I want the numbers that are less than or equal to 11, let's just kind of highlight on the number line here the ones that it would be. It could be, let's go to my highlighter, there we go. It could be 11, so this would be a solution for n. This would be a solution for n, because if you plug it in, you get 15, and that is less than or equal to 16. It could be 9. Okay, that would be 14 is less than or equal to 16. It could be anything less than that. It could be 8 or 7 or 6 or 5. Because remember, the goal here is that we want n's value to get us something that is less than 16 or equal to 16. So 11's as high as n could be, but it could also be something less than that. So if I look at my number line here, I want to put a closed dot on 11 because n could be that. And then I want to show my solution set, which would be all the numbers going this way. All right, that would be my graph of this particular inequality because it shows me all the values that n could be. It could be 11, it could be 10, it could be 9. Notice it couldn't be 12 because if I plug a 12 in, 12 plus 5, well, that would be 17, and that is not true then. 17 is not less than or equal to 16. So it's these values here, and just a reminder, it's a closed dot on 11 because it actually could be 11. Now, if I want to check this, if I just plug in some of these numbers, you can see this to be true now. 11 would make the inequality true. 10 would make our inequality true because that'd be 15. And then, 9 would work. I could keep going. 8 would work, 7 would work, 6 would work. All of these would work for the value of n. Okay, and this is what this graph is showing. And it could be 11 or anything less. Now, that's a lot going on here, but a reminder, we want to solve the variable. We want to figure out what n could really be. So that's the solution right there. We can graph it, we can check it. Let's do the same thing for number 2. C minus 9 is greater than 14. So if I want to get my variable by itself, look at what's happening to the variable. We're subtracting 9. So we want to get rid of that. So what do? What's the opposite of subtracting 9? Well, we want to add 9 to both sides. Again, you have to do it to both sides. Think of this as a little line right here. You want to do it on the left side of that symbol and on the right side of that symbol. So these would cancel out, and you're left with C is greater than 23. That would mean that the value of our variable is more than 23, okay? Because if I plug in, something that's more than 23 to this, now it's true. But think about what happens if I plug in 23. If I plug in 23 right there for C, 23 minus 9, well, that's 14. And 14 is not greater than 14. So that's why this one has to be greater than 23. It cannot be 23. And for that reason right there, if I was setting up a number line, I would use an open dot on 23 this time, okay? I would just put that right about there. And I want all the values that are greater than 23. So think about which ones those are. Okay, we've already established it cannot be 23, but it could be 24, it could be 25, it could keep going, it could be 26 or 27. So that's our solutions for C, all the numbers that are greater than 23. So we want the arrow showing all the numbers that are greater than 23. So we're just going to do that, okay? That would be our solution set, anything greater than 23. Now, if I want to check this, I want to try some of those numbers that are greater than 23. So the first one I tried was 24, I think. Yeah. If I plug in 24, I would have 24 minus 9, and that is 15. So this is true. If I keep going, I could try 25, just to prove the point here. 25 minus 9, well, that would be 16. That's true. If I try the next one, I could try 26, and that would be 17, and that is true. So my values here could be C greater than 23. Anything that's more than 23, 24, 25, 26, and so on. That's our solution set. So we're solving an inequality, we're graphing it, and then we're checking to make sure that it does work. There's a lot going on here, but we should be pretty comfortable with this because it's a lot like solving one-step equations, which we've already done. Now, in number 3, let's look at this one. 12g is less than 48. Again, we want to get our variable by itself and think about what's happening to it now. It's being multiplied with 12. So we want to undo that. We want to use the inverse operation of multiplying, and that would be dividing by 12. I divide both sides of that problem by 12. Now this 12 cancels out. We're just left with our variable. And on the right side, we have an answer of 4, because that's what 48 divided by 12 was. So this is really the solution to this inequality. G needs to be less than 4. So if I go to my number line down here, G needs to be less than 4. Now think about it. That's my dot's going to go on 4. That's kind of the rule here. The dot's going to go on 4, but the question is open dot or closed dot? Well, it would be an open dot if it can't be 4. It would be a closed dot if this could be 4. Think about what happens if you plug in a 4. That would be 48, and that is not less than 48. So we cannot include 4. We want an open dot on 4. Now, G is going to be everything less than that. So that, again, if I highlight which ones it could be just to show here, the ones that are less than 4 would be 3, and 2, and 1, and 0, and so on, all right? So that's the direction my arrow wants to go. That's my solution set. Everything less than 4, all right? So you should graph that. And then we can also check it, okay? Think about what numbers we can plug in. Well, let's plug in the ones we highlighted. If I plug in a 3, well, that would be 12 times 3. Well, I know that's less than 48 because that's 36. Well, then I could plug in a 2, that would be 24, and that's true. If I plug in a 1, well, that would be 12, and that's true. I could plug in a 0 or some negative numbers because it really keeps going, but these are all true now. But if I tried a 4, that would not be true. Or if I tried a 5 or a 6 or a 7, this would not be true, okay? So that's the solution for number 3. In number 4, we have this value, p divided by 3 is greater than 9. Well, I just rewrote it first, p divided by 3, just to let you see this is really division. We should kind of understand that and be okay with it. So I just rewrote it this way. And again, we want to get the variable by itself. So to undo division, we multiply both sides by 3. This will cancel out. We're now left with just our variable. And on this side, we have an answer of 27. So for this one right here, we would say that the solution for this one is that p is greater than 27. Because if p is 27, now we're kind of working with this a little bit more clearly. So on our number line here, we just want to set up that sequence of numbers. We want something that's around 27, so I did 26, 27, 28, 29, 30. And if you think about this, what if p is 27? 27 divided by 3 would be 9, and 9 is not greater than 9. So we want to use an open dot on 27 because our solution set cannot be 27, but it will be everything more than 27. So I want 28, I want 29, I want to go this way with my arrow, with my solution set, okay? It could be 28, it could be 29, it could be 30, and here's how we can check that. Well, if we plug in a 28, We get 28 divided by 3. And that goes into this 9 times with 1 left over. So that's like 9 remainder 1, or 9 1/3. And that is greater than 9. If I plug in 29, well, now I get 9 with like 2/3 left over, or remainder 2. Okay. If I plug in 30, well, now I know that's 10. Okay, which is greater than 9. So all of the numbers going up from 27 would be solutions for this variable in this context. All right. Okay, let's solve a few of these here. If you look at this section right here. All right, so you see here, we're just going to work our way down this, starting with the second one, so the 2 on your left there. 7x is greater than or equal to 35. Well, if this is what I'm working with first, I want to get the variable by itself. So what do? We divide both sides by 7, because right now it's being multiplied by 7. So divide that side by 7 and divide this side by 7. And now we're left with x is greater than or equal to 5. So that's our solution for this inequality, okay? X can be anything that's greater than or equal to 5. That means it can be 5, it can be 6, it can be 7, it can be 8. All right, so there's your solution set right there. In the second one, if we have this right here, x plus 6 8/10 is less than 11 2/10, we want to get rid of adding 6.8. So we subtract that from both sides, and that will cancel out. This over here ends up with a value of 4 4/10. So x is less than 4 4/10. That's our solution for the second one. Yeah, it needs to be something that's less than 4.4. And the reason we know that is that if it is 4.4, we end up exactly at 11.2, and that is not less than 11.2. So it just needs to be something less than 4.4. It can be 4.3, 4.2, it can be 4, it can be 0, a whole bunch of options here, because again, inequalities have an infinite number of solutions sometimes. So there's a whole bunch of options. In this third one right here, x minus 5 is greater than 16.7. So I want to get rid of minusing 5. So I add 5 to both sides. And if I add 5 to both sides, that gives me my solution right here. X is greater than 21 7/10. So my value for x needs to be more than this, and that would make this over here true. All right, so we're solving one-step inequalities, and that is how things are going. In the fifth one right here, if we look at x plus 14, and that is less than or equal to 16, well, we want to get rid of the plus 14. So to do that, we subtract both sides with 14. That cancels out. Over here, that gives me an answer of 2. So really I have x is less than or equal to 2. And that's our solution. In number 6, 8 is greater than or equal to x minus 3. So we want to get rid of the minus 3. So we add 3 to both sides. This cancels out. This gives us 11. So we would simply say 11 is greater than or equal to x. All right, that's what this first one is here. Now, sometimes we just turn that around too, because we kind of like it when the variable's on the left side. So if I rewrote this, I could just flip them. But notice if I flip them, I've also flipped my sign, because I want 11 to be greater than or equal to x. So the opposite of that would be x is less than or equal to 11. So I could write it either of these ways. They're saying the same thing essentially. I want you to try 7 through 12. You want to go ahead and pause it, give those a good honest effort, and then come back when you are done, please. All right, check your work. Go ahead and pause it if you need to, but you can go ahead and see the solutions right here. All right, this last problem here. A business trip will be reimbursed 55 cents per mile. Mr. Jackson has a budget of $70 for the round trip. If he is traveling to a town 61 miles away, will he be under or over budget? Prove our thinking. So I included a little map here just to give us a visual. Basically, he's getting reimbursed for traveling. They're going to pay him 55 cents for each mile that he's driving. Well, they tell us that the other location is 61 miles away. What you want to remember, though, is that he's got to drive there and he's got to drive back. So really, he's driving 122 miles, okay? Half of them there, half of them to come back. So for all of these miles, he gets reimbursed 55 cents, all right? So that sounds like multiplication. We also know that he has a budget of $70 and he doesn't want to go over that budget. Let's look at what we could do here. We could think of this as 61 miles times 55 cents. That would be all the miles there plus all the miles back, and we want that less than or equal to 70. All right, that's the goal, is to stay under 70 bucks, or to not go over it at least. Now, another way to think about this right here is to just say, you know what? We know he's doing 122 miles. Let's add those 61s. 122 miles times 55 cents. That's probably the easier way to think about it, for me at least. If he's getting 55 cents for each of these miles, we really are kind of hoping that that's less than 70. And if we multiply that out, if we actually multiply these two numbers, that comes to $67.10, which we know that is less than or equal to 70. So the question up here was, will he be under budget or over budget? Well, he is under budget, okay? He's about $3 away from his maximum amount. So we would simply say Mr. Jackson will be under budget. There's a lot going on there, but we were basically thinking about an inequality because we knew we didn't want to be more than 70 bucks. So we can think about this with the trip there and the trip back, or just the total miles, grouped together in one number. But bottom line is he ends up being under budget. Okay, he's about $2.90 less than what his maximum number was. All right, let's summarize today's lesson. Solving one-step inequalities is a lot like solving one-step equations. Okay, it's pretty much the same approach. You want to isolate the variable, you want to balance the problem, and you want to come up with your solution. And we use inverse operations to do this. All right, we use inverse operations to do it. The only other thing I would say that this is not written there, inequalities have a whole bunch of solutions. All right, that's why we're using an arrow on a number line to show us all the ones that it could be. Equations just had one solution in a previous lesson, but inequalities have a whole bunch of solutions. All right, that brings this lesson to a close. Thank you very much.